Charged particles hit some materials and then X-rays are emitted
to the nanometer dimensions, which is rarely done in the world.
Gives us the new approach and the better quality and sensitivity.
To produce a beam with its diameter in a nanoscale, nanometers.
We will be able to see inside the cells.
So we really look forward to see this Nanobeam line in action.
I'm not a scientist, I'm an engineer, and my job is to develop functional, useful things for scientists.
Zdravo, ja sam Mirjana Vasić, dolazim iz Srbije i po zanimanju sam hemičarka.
Moje ime je Boštjan Jenčič, sem fizik, zaposlen na Inštitutu Jožef Štefan, odsek za fiziko nizkih in srednjih energij.
Το όνομά μου είναι Γιάννης Κρεμίτσας, είμαι 23 χρονών, είμαι φοιτητής φυσικής στο Πανεπιστήμιο Ανίνων της Ελλάδας και ο λόγος που έγινα επιστήμονας είναι διότι από μικρός είχα μεγάλο ενδιαφέρον να ανακαλύψω τα μυστικά του σύμπαντος και το τομέα της φυσικής είναι ένας τρόπος να εξηγήσω τον κόσμο.
Moje ime je Matej Skobe, prihajam iz Ljubljane, glavnega mesta Slovenije. Na Inštitutu Jožef Štefan sem zaposlen kot inženir na pospeševalniku.
Hola, soy Esther Punzón Quijorna, soy española. Y decidí ser científica, bueno, imagino que como muchos de nosotros, porque cuando era niña, era una niña que se hacía muchas preguntas y lo sigo haciendo. Y la ciencia te da herramientas para entender mejor cómo funcionan las cosas y también para responder algunas de esas preguntas.
Sem Mitja Kelemen, prihajam iz Slovenije in trenutno sem doktorski študent na Inštitutu Jožef Štefan.
Od uvek sam bila fascinirana životnom sredinom i sama pomisao da na bilo koji način mogu da pomognem ovom stanju u kome se trenutno nalazim i daje dovoljno razloga da se bavim ovim čime se mi bavimo i znanjima u novim kojima mogu da prinesem.
Znanstvenik sem postal, ker mi je všeč ta nepredvidljivost in vznemirljivost znanstvenega dela, torej nikoli ne veš, ali boš dobil odgovore, vprašanja ali mogoče kaj vmes.
Že od majhnega me je veselilo raziskovanje in odkrivanje novih stvari, zato sem se našel v svetu fizike in s tem odkrival nove stvari v naravi.
I became an engineer because I would say for me that I'm precise and organized, and engineering is all about this.
The project is about developing and constructing a new, highly advanced experimental setup. The project is called a Nanobeam. This is the new beamline. So basically what can be done with this beam is very detailed measurements because of the small scale of the beam.
We can do many things with focused ion beam. For example, material analysis or material modification and so on. Mostly we will focus on material analysis, so biological tissue analysis. We will do either a method called PIXE, which is elemental imaging, so imaging of individual atoms within the tissue, or we will do MEV-SIMS, which is molecular imaging of tissue. And we can focus this beam to very low dimensions, so we can actually observe tissue on subcellular level.
We will research the biological tissues in the different plants and also the biomaterials.
The real success will be that everything works as we planned, because this is not a trivial task. You have to align all the components really fine together so everything works as planned, and the ion beam is really focused on such a small scale. I think we don't even imagine how small this scale is. We know that 1 millimeter is quite small already, and then 1 micrometer is 1,000th of 1 millimeter, and then 1 nanometer is 1,000th of micrometer. So this is unimaginably small, I think, for most people, including me.
If you imagine that squeezing something on a small space, but still have enough of particles inside that space, this is one of the main challenges that we try to conquer here, is to find the path how to do it.
In the first phase, we developed, ordered and assembled all mechanical, electrical and pneumatic components. And in the second phase, it's our task to minimize and prepare and calibrate the beam with our installed equipment. I hope that everything will fit together.
Protons used as our nanobeams are created in the ion source, which is behind me. Inside this white cabinet, we burn hydrogen plasma and extract negative hydrogen ions from it. Negative ions are firstly accelerated with a low voltage against the terminal of our accelerator, in which they are accelerated to the high energy that are needed in our nanobeam. Protons for our nanobeam starts here at the beginning of our experimental hall and end up at the far side, around 20 meters away in the chamber of the nanobeam. We reach 10% of speed of light.
And is used for different measurements such as PIXE, which stands for particle-induced X-ray emission. So what basically happens is charged particles hit some materials and then X-rays are emitted. So through different software and detectors, we can analyze these X-rays and correspond the energies to different materials and different elements.
Here we have the sunflower's root, which are prepared for the PIXE measurements, and they are cut on the tiny slices, which are actually put between the two foils. The beam is coming through this sample, and we are actually measuring the X-ray which are coming from the electrons.
The detector and all the electronics takes X-ray, and depending on the energy, put this X-ray in different boxes. So at the end, what we have is like a spectrum with all the peaks, and each peak corresponds to one element.
With the focused ion beams, we are able to map the distribution of elements. And as you can see on those pictures, we obtain elemental maps. With the PIXE, we can show why the whole grain food are much nutrient denser than white bread, for instance. Because as you can see on the maps, the calcium, for instance, is concentrated only in the husk of the buckwheat grain, and even phosphorus is concentrated in the embryo. And the empty parts that you see on all the images is where the starch is saved inside the grains. And during the milling process, all this husk and embryo is removed from the flour, and we are left only with the starchy part. And this work was done on our microbeam, and now the questions arise, what is happening inside, for instance, embryo or the husk on the cellular level. So this is why we are building now the nanobeam, which will help us to answer these questions. So we will make a zoom into smaller parts and look at it in more details.
But it is a little bit too dark now.
Now everything is working. We have all equipment in the house. Everything is installed. One of our biggest improvements was a table or a platform with active damping. If you have disturbances on this platform, it can rapidly dump them. This is important because you need to have a steady camera. So, for example, if you have disturbances, this camera will move all the time.
So far everything is working as planned, but we still need to fine-tune the beam focusing. We need to align some lenses here or provide some other modifications in order to achieve the desired resolution of the ion beam.
Yeah, I'm very happy with the result. The Nanobeam looks really nice.
Do you see the beam?
No, not yet. Now we see it.